Hello and welcome. My name is Cindy Heitzman, Executive Director of the California Preservation Foundation. Thank you for joining this webinar on Sound Advice, Improving Acoustics in Historic Buildings. The format for today's webinar will include an hour presentation followed by time for questions and answers. There is a toolbar on the right side of your screen. If you have a question at any time during the presentation, please type it in the box and I will either reply to you or hold a question until the end for the panelists to answer. Please refer to the audio tab in the toolbar and select if you are listening through your telephone or speakers. To hide or unhide this toolbar, click on the orange arrow. Please adjust your volume on your computer or your phone. Today's presentation will be by Amanda Higbee and David Schwind with Charles Salter Associates. Amanda Higbee joined Charles Salter Associates with as an acoustical consultant after finishing a degree in architectural engineering at the University of Texas at Austin. With a passion for historic preservation and sustainability, she has focused her work on these types of projects, enhanced by involvement in the local USGBC chapter and various preservation groups. Her project experience has primarily included multifamily housing, offices, theaters, and educational facilities. Project highlights include the Twitter offices, Fort Mason, ACT Second Stage Theater, and the Geary Theater, all located in San Francisco. David Schwind has been consulting in acoustics since 1975. He was the first to graduate from Purdue University as an acoustical engineer in interdisciplinary engineering. His expertise includes room acoustics design, sound isolation, and noise and vibration reduction for buildings, equipment, and products. In 1995, the Audio Engineering Society elected him Fellow for his contributions to architectural acoustics and sound system design. His ongoing and recent project experience with historic buildings includes the Fox Theater in Oakland, the Walt Disney Family Museum at the San Francisco Presidio, and the old administration building at Fresno City College. Thank you for joining us.
And thank you, Cindy, for inviting us to participate in this webinar. And thank you to all the attendees for tuning in. And Amanda and I are going to give you a presentation on acoustics in historic buildings. I guess we're having a small problem advancing the slide.
Cindy, you might have to switch over the screen here.
For reasons we don't understand, we are not able to advance the slide.
Okay. Try it now.
With that. No, I apologize. Worked fine earlier. Cindy, can you take the control? I can just tell you when
we
we
can
need
just tell
to
you
advance.
next. Yeah.
I can.
Not advance it.
Okay.
We'll start out with a small introduction of our firm. Charles Salter started the firm in San Francisco in 1975 as a sole proprietorship. I joined him in 1984, and today we're a firm of approximately 52 people. Although we started out as acoustical consultants only, today we consult in acoustics, audiovisual, telecom, and security. For this presentation, there are AIA CEU learning credits available, and for those we need to have learning objectives, and so we have 4. One is acoustical terminology. These are all 2- and 3-letter acronyms: sound transmission class and noise isolation class. The first two relate to sound isolation through a wall, ceiling, or floor, window, or door. The next one, noise reduction coefficient, is a rating from 0 to 1, which rates sound absorption of a material. And the next two rather, relate loudness. NC, or noise criteria, rates loudness in buildings. And dBA, or A-weighted sound pressure level, is the rating for outdoor noise that's commonly used. ASHRAE is the standards organization that describes noise criteria. There's also another type of criteria called room criteria. Both are listed there. ASHRAE is the group that mechanical engineers typically join if they're involved in ventilation, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. The third item is reverberation time. We'll define what it is and why you should care about it, but it basically is the liveliness of a given room. So you tend to think of this in concert halls or theaters or even conference rooms. And finally, the fourth item is sound flanking, and this is a form of leakage around our sound isolated or sound rated assemblies. So this sound flanking would reduce the STC or NIC. Okay, we can advance.
Cindy, I think you're going to have to move the slides forward for us.
Thank you. Going on to architectural acoustics, there we cover 4 main areas. So we think of room acoustics as being the reverberant and/or sound absorbing nature of the interior. We can talk about sound isolation, as I mentioned, using the STC and NIC through walls, floors, ceilings, doors, and windows. And we can talk about environmental noise from exterior sources penetrating the building shell. And finally, building systems noise, having to do with everything we put into buildings that generate noise and can cause disturbances. Next slide, please.
And historic buildings pose specific challenges for acoustical engineering. And the first is going to be materials and appearance. When we deal with this issue, we're often trying to match the period aesthetics, trying to pick acoustical materials that don't look inappropriate for the space. The other issue is going to be not disturbing existing historic elements. There may be architectural features that are being preserved, and there's limited space to apply new acoustical treatments. The second issue is going to be a changing noise environment. You may have a noisier building than the original functioned as, and such as a music venue that used to be a warehouse. You also can deal with a louder exterior environment than originally, and that's going to be something like a new roadway, expanded roadway, a new flight path over the building. The third issue is going to be adaptive reuse. You may have new interior noise criteria. The building may be functioning as something that needs to be quieter than it did before. This is going to come into play especially with environmental noise and HVAC noise, getting that NC rating down where it's appropriate. The other issue is going to be an installation of building systems. Oftentimes you may be installing a larger HVAC system or something along those lines, and this can cause problems for noise. Next slide, please.
Okay, Amanda, I think you can take control from here too.
Oh, great. Is it working? Oh, it is. Cool.
Room acoustics. So this is the first of the 4 elements that we'll be discussing as part of architectural acoustics. And as I mentioned, this can be thought of as the reflectivity within a given room. And here we see some ray diagrams from a computer model, from a source on a stage of a performing arts venue to a receiver. And this was an analysis that's in the appendix of a book we wrote. And we'll talk a bit more about that in a few minutes. Room acoustics basically is designing the building interior for aesthetic quality and pleasurable listening. So this would be analogous to picking soothing colors in a sense, if you're an architect. What it involves is the analysis of direct and reflected sound. So when we're standing outdoors, what we're hearing is direct sound mostly, and maybe reflections off the ground. But we are not enclosed, so we don't get walls or ceiling reflections. Now, speech intelligibility is something that's common to many building types, and it would be improved by reducing reverberation. This is really important. So we've got the example of poor speech intelligibility in a cathedral, where you have a 3 or 4 second reverberation time, versus excellent speech intelligibility in a really well-designed conference room or even a recording studio. So where we would concentrate on room acoustics is any place where speech or music or any other form of communication that's audio is to be transmitted to a listener. So you get spaces like theaters, concert halls, cinemas, restaurants, classrooms, courtrooms, places of worship. All of these can have a consideration for room acoustics. So what is reverberation time? Sometimes referred to as RT60. Well, it's the time it takes sound to decay 60 decibels when you abruptly turn off a sound source, or you burst a balloon or fire a starter's pistol or even a yachting cannon. These can all be used to measure reverberation time. There's an interesting story of acoustical history here. Modern acoustical engineering is really an invention of the United States. Wallace Clement Sabin was a physics professor at Harvard University, and he started getting interested in acoustics in the early 1890s, and by 1895, 2 things were starting to happen for him. One was that the Boston Symphony Hall was being designed, and he was asked to consult on that. And as we know, he did a very good job of doing his homework and produced what is today one of the finest concert halls. However, when it opened and the first European touring orchestras came, and these were smaller orchestras of about 60 players, the conductors panned the hall and declared it a disaster. Fortunately, Sabin did realize before he passed on that it was in fact a great hall. However, this debacle caused him to lose his tenure at Harvard. I've gotten a little bit ahead of myself. While he was at Harvard, he came up with this notion of reverberation time, and it all started because the dean noticed that the brand new seminar theater shown on the right had incredibly poor speech intelligibility. And Sabin's first observation was the incredible reverberation in there. He also noted that the space had a similar number of seats to the Sanders Theater across the street, which was part of the university. And he noticed the main difference was cushions on the seats, so fully upholstered seats versus wood benches. So he got his graduate students, and at night they would start bringing cushions across the road. And I'm sure people wondered, why are all these line of people going across the road with cushions? What he was doing was making measurements by adding cushions into the defective space. And he was making measurements in a very clever way. He didn't have a sound level meter because those hadn't been invented yet. What he did was he used a tuned pair of organ pipes. And what he would do is he knew that 2 organ pipes, in theory, should be 3 decibels louder than one organ pipe. And he built this box to sit inside so the absorption of his own body wouldn't affect the measurement. He knew that that could have an effect. And of course, he cleared his students out of the room. And what he would do is play one organ pipe. And he did this at night because he knew the background noise level would be very quiet. And then he would release the key and start the stopwatch or the clock. And when the sound had disappeared into the noise, he would stop the clock, note the time. And then he would repeat that using 2 organ pipes. So the difference between the 2 measurements was a 3 decibel decay. He would multiply that by 20 because he felt that the signal-to-noise ratio in the space was about 60 decibels. So that was fairly arbitrary. However, it's been standardized. So that's how reverberation time came into being. What did he do after he lost his tenure at Harvard after the Boston Symphony Hall debacle? Well, he went on to found the first acoustical laboratory in Illinois, the Riverbank Acoustical Lab. And this was funded by a gentleman named Fabian, who was a very wealthy textile merchant. And he was interested in acoustic levitation. And Sabin was less interested in that and really was interested in architectural acoustics. So he designed the labs around what he knew would be useful in the future, the architectural acoustics. The lab still exists today and is still a preeminent lab in the world. Another interesting historical side note is his fellow Fabian was asked by all his friends to write a book on textiles, which can be acoustically absorptive. And Fabian obliged him by writing a book. He gave it out at Christmas. The only problem was all the pages were blank, and it was titled Everything I Know About the Textile Business.
Are we stuck again?
It appears we're stuck again. My apologies.
Thank you.
Thanks very much. So, as I mentioned, reverberation time is the time it takes for sound to decay 60 decibels, and you can see that decay in the graph to the right. So you have sound pressure level on the vertical axis. You shut off your loudspeaker abruptly, and you can listen to the sound decay in the room. One decay is the red curve. However, if we average many decays together, we would get something more like the black line, and that's much easier to determine the slope of and determine the decay rate. So what determines reverberation time? Well, Sabin discovered that it's directly proportional to room volume, so one would expect the cathedral to have a much greater reverberation time than a conference room due to its size. However, he also discovered that it was inversely proportional to the amount of cushions or sound absorption that he had brought into the theater. So that's something to keep in mind. So if you wish to reduce reverberation, you can add sound absorption, or you may even be able to decrease the room volume just a little bit. This is a graphic showing reverberation time as a function of use. So on the bottom left corner we have low reverberation times for recording in broadcast studios, and you'll notice right in the middle of the graph there's something, a long bar for churches and cathedrals. So that spans from, the whole graph spans from about 0.2 of a second up to 2.6 seconds. In fact, cathedrals can go out to 10 seconds. So from graphs like this in acoustical textbooks, you can get a rough idea of where your space should fit in. So this is an older graph. It shows cinemas at somewhere between 0.8 and 1.2 seconds. We learned in the late 80s from Tom Holman at THX and Johan Allen at Dolby that in fact that needs to be much lower. So we talked about direct sound as being as if we were outdoors. Even in a room, we can experience the direct sound field if we're close enough to the speaker. So in this little diagram, we can see the sound lines labeled D as the direct sound, and we see one reflection represented by the line labeled R. In this case, that line could be a nasty echo because of the long delay path. You see the short D is much shorter than the long R line. Now, lined up underneath this, we have another graph. We have distance along the horizontal axis and, again, sound pressure level on the vertical. And you can see that sound fields naturally get lower or reduce when we move away from the person doing the speaking. However, in a reverberant room, which all rooms do have a reverberant field, you'll eventually hit a point where the direct and the reverberant field are equal. And you can see a little dashed line there, and that's right where that listener is sitting up above, you see. So he's in a pretty good spot because he's getting probably enough direct field. However, the rest of the audience in this room is in the reverberant field. And the only way we can improve that, you see the little line that says increasing reverberation time? Well, if we decrease reverberation time, we will get a larger direct field covering more of the audience. So that's how the physics of this works. So in talking about reverberation, we tend to think about specular reflections first, which are those that bounce around like the very first room acoustics slide I showed. The angle of incidence equals the angle of reflection. The problem with those kinds of reflections, and that's largely from large, flat, hard surfaces like big expanses of drywall, plaster, glass, stone, those kinds of materials, is that they're very harsh reflections and they're analogous to glare and lighting. So when we design spaces, we go looking for absorption to control the reverberation time to an appropriate level and diffusion to prevent this glary, harsh type of reflection. So absorption, you can easily think of an anechoic chamber, which is pictured there on the left, and it is usually a porous material, usually a textile type of material, such as a mineral wool, a fiberglass, or cotton bats. Cotton bats have kind of gone full circle. That was the original sound-absorbing material back in Sabin's day, and wool also. And now we're getting back to those natural materials for lead points and sustainability and renewability. On the other side, we have the idea that we don't want specular reflections, but we want reflectivity. And so we shape a surface in a certain way. You've seen these convex and concave surfaces, concave usually being the preferred. And we also have this thing here, which is a special diffuser called a prime root diffuser. There's a company called RPG that has done a lot of work with that kind of thing and offers quite an array of products in this line of room acoustics. We're mostly familiar with sound-absorbing panels, and these are almost commodity items today. You know, we think of Armstrong and Owens Corning and these sorts of companies, the big fiberglass manufacturers. And these things can be wrapped in the porous fabric, often like a Guilford FR701, which is fire retardant. The porosity means that we can allow air to pass through it. So a test of a porous fabric is if you put it up to your mouth, can you blow air through it? So those are very common and fairly economical. And probably the least expensive sound-absorbing material is a lay-in ceiling. However, there's a lot of other ways that we can have a different appearance for sound-absorbing material. So it doesn't have to be an acoustical tile ceiling or a fabric. Nowadays we can have perforated wood, slotted and perfed metal. There's porous sintered metal. So there's a lot of coverings that can be used to conceal the sound-absorptive material. Of course, the covering has to be sufficiently porous. And sometimes the coverings act like a filter. So we need to be careful about the selection of the covering.
Oh, 1, 2, 5. Oops. So there's specific historical challenges in room acoustics, and the first being existing historical surfaces and elements, those architectural features that really make the historic space beautiful and special may not be something the architect wants to remove. So you're dealing with these typically old hard plaster elements, and you're also trying to find aesthetically appropriate acoustical materials to fit into the remaining spaces, typically trying to add absorption into these spaces. The other issue is repurposing spaces for amplified music and speech. Oftentimes, a space may be fairly reverberant, a lot of that old hard plaster, and you get a muddiness in the space by music and speech being loud, and you don't want a lot of reverberation because it starts almost being echoes where you can, where it's laying over on top of itself and you can't hear the person anymore the way it's meant to be. Some of the solutions to room acoustic problems are shown on this slide. These are going to be the products with historic style. Luckily, there's more and more options being manufactured all the time. A pretty cool one that's fairly new is the Armstrong Metal Air, and it's a perforated panel that can come in all these colors, and it really looks nice in a historic space, and you can really match it up with what you're trying to do aesthetically. On the right corner is the cotton bat that David talked about earlier. It's a recycled product, so it's also considered a nice green product, and it really presents a historically authentic acoustical environment. You might get your space back to what it would have sounded like when it was originally built, because they probably used cotton bat as absorption originally. We also find that adding drapery and carpet is a pretty good solution. Drapery can look really nice, especially in theaters. Carpet can be applied in restaurants and along the aisles of theaters and whatnot. And we're going to come to our first case study. This is Cavallo Point in Sausalito, California. It's a military fort that was converted to a luxury lodge. And this picture is their restaurant. And they've done a lot of good things in here. Most people can relate to restaurants being an unpleasant, noisy environment. We've all been in those restaurants that are concrete and glass, and they're really pretty, but they're not that pleasant. Here they've been able to add carpet down on the ground, which adds a lot of absorption, and then the draperies are all scattered all over. You can double side these, you can line them to add mass. They typically range from 18 ounces to 16 ounce velour draperies, and you can add airspace between them and the wall to add even more absorption. Lastly, up on the ceiling, you can see some a tin ceiling. This is not the perforated tin ceiling, but it could have been an option to replace it and still come out with the same look. Our next case study is a theater that's in California, and it's a movie palace from 1928. It's been converted to a music venue for both amplified and acoustic music. There's some cool things in this one. One option that they've gone with is applying absorptive materials behind this acoustically transparent spaces. So without disturbing the existing architectural elements, they were able to add absorption. Adding tapestries back in these openings has also been a good option. There's been absorption added up here, which, or it talked about added up here, which is nice because it's not in the line of sight if you're down in the audience. Also adding draperies is an option for something like this, but notice it's important to find a spot that's not architecturally important, so these flat plaster areas. And on to the next.
Thank you. Cavallo Point was a project that Architectural Resources Group participated in as an architect, and the theater is Architectural Dimensions in Oakland and ELS in Berkeley. This is the Grumman's Chinese Theater, the historic landmark, also dated to 1927. So that's the year that sound first came out with motion pictures. The developer of this project was concerned that maybe it wouldn't be successful as a film house, which it actually has been remarkably successful as for the entire time, but it was built as a vaudeville house just in case. So there is a stage house behind that big curtain. Time has moved on with sound systems, and when JBL replaced the system to THX standards, subsequent to the architectural remodeling of the space, we were called and asked if there was anything further that could be done to enhance the audio. So it was more of an audio system issue than anything. And we made a lot of measurements in there, both the audio and acoustics. Of course, we can't touch the historic surfaces around the columns, but there are some pretty clever ideas here. If we go between these columns, you'll see there's a drapery. Those are power operated. So here's another one. And when the film starts, those are shut. So it's decreasing the volume of the room by closing off the entry galleries on both sides, and it's expanding the area of sound-absorbing material. So that's a pretty clever idea. Also, they've taken these niches and put drapery, in them up here. And down below, this is a drapery-like material with thick sound-absorbing material behind it. And any gaps where there are air spaces here, gaps in this filigree, sound-absorbing material can be placed above that. And finally, what we found mainly was that part of the audio muddiness was caused in the subwoofer range. So this was down anywhere from 20 to 80 hertz. There was a kind of an echo being generated between the concrete floor, which is carpeted, and the ceiling. The difficulty with the carpeting is it's not absorptive at low frequencies. It's just not thick enough. So we discovered that they had neglected to treat the drywall ceiling. They had simply painted it black in this area. So we put we actually were able to drop a black ACT ceiling in that area to pick up the low frequency absorption quite a lot. And it really improved the audio, getting rid of this muddy quality to the sound. So we're going to go on to our second major topic, and that is sound isolation. So now we're switching away from just a single room and talking about sound that's transmitted from one room to another. So this is commonly thought of as speech privacy between offices, or sound isolation between apartments are both pretty good examples. It can involve either airborne or structureborne sound, and a lot of times we call structureborne sound impact sound. So that's the sound of people walking on the floor ceiling assembly above you, and it has a rating system that we'll describe in a moment. So by improving sound isolation, we can obviously improve the peace and quiet of the space, but we can also improve speech intelligibility between the offices, improve the speech privacy between offices, and this can apply in a very wide range of buildings, from hospitals to recording studios and everything in between. So how we tend to think about any acoustical transmission is a source, a path, and a receiver. And this is pretty fundamental to all of our thinking when we go to a job site or we're presented with a new building. We start thinking about these. And, you know, we really think about buildings a bit differently than architects. Architects think about the flow of people and goods into the building and out of the building, and they think about congregating like things together, and those are all great thoughts. The part that we can bring to the planning stage is thinking about what can happily coexist together and what does not want to be together. So what is noisy that would disturb something that is quiet? And that's what we see here in this picture. We see a noisy machine separated from somebody's dwelling, presumably, because he has a phonograph. This must have been a long time ago, I'm judging. Anyway, we can see that the machine noise could be masked by the phonograph if he plays the phonograph loud enough. On the other hand, the opposite could also be true. If the machine is incredibly noisy and there's a very poor wall there, the machine noise could mask the noise or the sound created by the phonograph. So we've introduced the concept here of sound masking. So it's a noise that would be used, someone used to describe it as acoustic perfume. It's to cover up other unwanted noises. Now, two of our learning objectives were the sound transmission class and the noise isolation class. These are ASTM defined and ASTM E90, talking about airborne sound transmission in buildings. And STC is a lab rating. It's usually a single number, like let's say STC 45. That would be a very good window and a pretty good door. And a not so bad wall, but not a great wall. A typical office wall might be STC 35, whereas a double stud wall between condominiums might be STC 55. So a change of 10 points in this rating system is either a doubling or halving of loudness. So if you increase 10 points, you're actually decreasing the loudness, because this is attenuation. STC is an attenuation, so you want a big number for better attenuation. Noise isolation class is similar to STC, and it's what we generally measure in the field. STC is really trying to measure the acoustic energy flow from the source room to the receiver room, whereas noise isolation class differs in that it's trying to measure just the difference in sound pressure level from the source room to the receiver room. In other words, the amount of attenuation the tenant actually enjoys. So, what is this impact noise business, structure-borne noise? Well, it's created by people walking around upstairs or somebody banging on the wall with a hammer, or even very loud airborne noise can be transmitted structurally. So we have a device called a tapping machine, which is unique to our business. It has 5 50-gram hammers that drop repeatedly on the floor, and it creates a syncopated rhythm. So it's a known source of impact noise that puts a known amount of energy into the floor. And we use that as a standard device to measure the impact insulation class. Again, this is an ASTM standard, and you move the tapping machine around in various configurations, and you move your microphones around to get a spatial average in the receiving room. Again, this number gives a better rating, so more sound attenuation, the higher the number. So 50 IIC would be better than 40 IIC. In residential buildings, the International Building Code calls for assemblies to have laboratory ratings of STC 50 and IIC 50, and to achieve NIC 45 and a field IIC of 45. That's pretty much throughout the country. This has been true in California actually since 1974. So this is another learning objective, flanking paths, and these cause excess sound transmission. If we can eliminate the flanking paths, we're going to more nearly achieve the ideal performance out of the assembly. So a moment ago, you noticed that when the International Building Code specifies STC, they allow a 5-point degradation to the field rating of NIC. That's pretty typical. We can't avoid flanking 100% in actual buildings like we can in the laboratory. So one of the big issues in every wall are junction boxes, and the typical solution is to apply a caulking pad to the back. And the reason that they're a problem is they interrupt the layer of mass on the drywall, but they also have air holes in the back, so any air transmission path is definitely an acoustical leak. Also, unsealed head and sill conditions in wall assemblies leak sound. They can create incredible flanking paths causing up to 10 or 15 dB degradation. So that's why we always specify acoustic sealant to seal that up. Of course, if you put your junction boxes or mirrors in the residence back to back, if they have cabinet mirrors, you can talk right through them. So that clearly isn't meeting the required NIC 45 in residential. So we would back into those kinds of things in drywall. So it's a lot like fire rating. If you think of some of the things you do in fire rating and smoke rating, a lot of that is true for sound rating. So sound rating and sound isolation are really the same thing. Now, what are some of the physical characteristics of wanting to improve the sound isolation or STC? Well, we can double the mass. So if we have a window, we could double the thickness of the glass. And we would expect maybe to get somewhere in the range of 4 to 6 points. In theory, we should get a 6 dB improvement, but that doesn't always happen. If we double the airspace, so if we build a wall and we use 3 5/8 studs, and then we come back and we use something that's almost twice that much, we could maybe expect a 3 or 4 dB increase. In some cases, if we decouple the studs, we might get a 5 or 6 dB increase. Now, for something to be sound rated, it really must be insulated and caulked. And here we're talking about the insulation. So if we just have an ordinary single stud wall and we add insulation, we can expect maybe a 2 to 3 dB increase. Now, if we start increasing the number of attachments, and so this is sort of more academic here. For instance, if we start applying an excess number of screws to the attachment of drywall, we'll actually start decreasing the STC rating. Conversely, if we're in the lab and we want to cheat a little bit and get a really terrific rating out of our wall, we might use very few fasteners, even substandard. We've seen that done. So if you have an isolated construction, meaning something using a resilient channel or something like a resilient channel, Kinetics makes something called IsoMax, and there are other similar products using rubber elements. When you add the insulation into assembly with that kind of isolation, suddenly the insulation's worth a whole lot more. Now we're getting a 5 to 10 STC point increase. You can generally say that staggered studs would be comparable to the performance of a resilient channel using the same number of layers of drywall. Actually, we prefer the staggered stud if we can use it because resilient channels are subject to malinstallation. Through lab testing, it's been discovered that light gauge metal studs, in particular 25 gauge studs, outperform heavier gauge metal studs, and that's because they are more resilient, and they wind up giving a rating comparable to a wood stud or a stiffer steel stud with a resilient channel. Now, we all tend to think of masonry and adding a lot of mass, but just using masonry on its own really doesn't do the job. You need to fill it with grout to get the mass up on the average, and you also need to seal the porosity of it. And that can be done with a waterproof coating or paint or plaster. And finally, if you want enhanced low-frequency performance, that is really the hardest thing to get. So if you were next to a machine room and you had a residence nearby, you would want double studs. So, or a CMU wall, something that will have better performance in the low frequency range. Now, STC, unfortunately, only rates down to 100 hertz. It ignores everything below 100 hertz. So this really starts to address issues that are not addressed by the standard rating system.
Then there's specific historical challenges in sound isolation. The first is going to be limitations of existing assemblies. You may have an existing wall that can only be treated on one side or the other due to architectural elements. Another issue may be wood structure or otherwise subpar structure acoustically. Wood itself tends to be creaky and not have great sound isolation properties. There's also a problem with intersections of existing and new structures. You may be butting up a new partition up against an exterior mullion wall or brick wall that's been deteriorated a little bit and have trouble sealing that intersection. One of the solutions that we can use in sound isolation issues is just good planning. We call it anti-proximity. Don't put loud things next to quiet things. Unfortunately, this is often restricted in historic restoration. Another solution can be various construction solutions. You can do drop ceiling for floor ceiling noise, or an underlayment under any hard floors, hardwood floors, tile. Another option is furred walls, especially if you can't deal with a wall because of architectural features or structural issues that can't be moved. You may want to make it a sturdier acoustic wall by furring it out using resilient channels, as shown in this picture, or resilient clips. The other approach, of course, is sealing those assembly intersections airtight. Lastly, if you run out of other options, you can apply sound masking, which will help with speech privacy. It's introducing noise into the background, just white noise, that will help drown out other noises that are more annoying. Our first case study for this is the Battery. This is an industrial building. It's converted to a private social club. This is actually where the Salter offices were originally in the 70s. This is in San Francisco. It's a wood frame building with a restaurant in the bottom. There will be a private club in the middle and hotels, hotel rooms up in the top or residences. There needs to be a lot of acoustical separation between these floors, and our approach to that was these spring isolators for the drop ceiling, which really provides a greater level of acoustical separation than just a plain drop ceiling you might see with ACT tiles. Next case study is Ghirardelli Square. This is 4 buildings that are up in Fisherman's Wharf in San Francisco. It was the old chocolate factory, and it was converted to luxury timeshares. The buildings are from the 1890s through the 1960s when they were constructed originally. You can see here the issue of the deterioration of the grout, and the brick's been worn down unevenly. And you have a partition being built up against it that wasn't properly sealed. We came in and tested it after construction, and the noise was going straight through from one side to the other. But they were able to come in and finish these walls really nicely, sealed up airtight against these exterior partitions. The environmental noise is our next topic. This is going to be reducing intrusion from exterior noise sources. This is typically done by long-term conducting long-term and short-term noise measurements, analyzing this to come up with noise levels that are existing outside of the building. We will then develop mitigation measures to meet applicable standards and minimize annoyance. This is going to be designing doors, windows, walls to deal with the exterior noise conditions of your building. The noise sources often include vehicular traffic, rail transit, aircraft, generators, and industrial noise sources. The first step with environmental noise is typically measuring the environmental noise, and this is going to be done with a weighted sound level. This is called dBA, and it's a filter that you run noise through that basically acts like the human ear. And the human ear really focuses on this 1 to 4K range. We're more sensitive there because most communication happens above the 250 frequency range. So these lower frequencies are really less important for human hearing, although it can cause rumbles and stuff, which is oftentimes what can be caused by traffic noise. Also, it's important to note here that trees and plants do not help with noise levels. On here we have the planning guidelines. Oftentimes these exterior noise levels are used to create this kind of topographical acoustical map. Then a city planner can come in and use these maps and a graph like this to decide where it's appropriate to build things like residential units or auditoriums. This is a Treasure Island. We designed that acoustical map recently. The historical challenges with environmental noise, often the changing noise environments, either exterior noises like noisy neighbors or new roadways. The other issue is adaptive reuse with quieter interiors, such as things going from factories to residences or educational spaces. One of the main solutions is going to be door retrofits. We can either recommend STC-rated doors or sound gasketed doors, but it's even possible to apply these sound gaskets to your historical doors. Doors are often a weak link for environmental noise. The other weak link is typically windows, and especially historical windows. Architects really like to keep these elements. They're often a part of a historic charm. So one of the main solutions for environmental noise is going to be this interior window sash, which will significantly reduce the amount of exterior noise coming into your building. Our first case study is a music venue. This is a mortuary that had been converted to a music venue in San Francisco. We conducted noise measurements using this box here, and the problem was that they were going to disturb their neighbors rather than noise from the outside coming into their building. This adaptive reuse was a problem. We were able to determine how thick their windows and their doors and what other updates they needed to their exterior to meet noise codes and have happy neighbors. The next case study is the Hallidie building. This is in downtown San Francisco. This is where our offices are currently. And it was one of the first curtain walls in America. It was built in 1919. And there's our solution to the very loud roadway that's right outside this was to build this interior window, give it a very large airspace, as you can see in here. And we got a very significant reduction in noise, about 20 dBA. Our next topic is going to be building systems noise. Building systems noise, really the goal is to create a quiet and comfortable environment. Engineering and consulting on the mechanical, electrical, and plumbing systems to help reduce the noise that's coming from these. Vibration disturbances are also an issue, and you really have to worry about noise both indoors and outdoors. There's noise codes restricting noise from your MEP systems, both indoors and outdoors. This is going to apply to pretty much all buildings that have MEP systems. We rate the noise from HVAC systems using noise criteria. We go in and we measure the background of the ambient noise in a space, and we're able to apply this noise criteria rating to it. And it's a curve that's weighted similar to the way we hear and to what noises are disturbing to us. We also use this to design and do calculations on a system that's not yet installed, and we're able to determine the appropriateness of your system for your space. This shows that different spaces have different NC level needs. The more sensitive they are, the lower the NC level needs to be. Another issue is outdoor noise restrictions. Oftentimes this applies to generators, and here you can see a generator shown on a rooftop, and it's an issue for it to be meeting the property line. Most cities have noise restrictions on how loud this can be at the property line. Typically the generator is going to need to be housed. Other equipment may need to be too. The mechanical structure-borne noise can be dealt with spring isolators or rubber isolators. You can see in the picture this is both up on a house and a space-saving spring isolator. Another issue with mechanical is going to be airborne noise. This is where the noise comes out of the mechanical equipment and comes to you through the air rather than the structure. It can come out of the diffusers or radiate out of the ducts, as shown here. Typically, this is dealt with silencers or duct lining. Plumbing is also an issue when you're installing new MEP systems, both for the restrictions in space, for there being enough space around your pipe, as well as pipe isolation from your structure, especially when you have creaky wood structure. And here you can see a spring in here. The historical challenges really involve being constrained by space and structure. You may have limited options for equipment location. It may need to be on a rooftop or maybe outdoors, or maybe in a mechanical room that's less than ideal location. You're also going to have minimal space. You might have minimal space for pipes, ducts, or vibration isolation systems in those springs and stuff. You also may create leaks in your space when you create holes in your assemblies for these new pipes and ductwork. Here is our first case study. This is the Strand. This is a theater in San Francisco, California. And because of the sloped roof, as you can see in here, we were forced to put the mechanical equipment right up in front. And due to sight lines in this parapet being an existing architectural feature, we have to put the unit on space-saving vibration isolators because there's such strict height restrictions on how far up that unit can be above the roof. This is a hotel in San Francisco, and you can see that by installing more HVAC systems, they're really forced to take advantage of space that is really less than ideal for their HVAC system, putting it right up next to windows. And this is able to be solved by making these rooms not necessarily something that is noise sensitive and adding thicker windows. Here you can see the issue of rooftop units creating exterior noise that may disturb this building where the picture was taken from.
Okay, we have a couple of more case studies. This was a project in the San Francisco Presidio that we were fortunate to work on with Page and Turnbull Architects. And the big issue here for acoustics was this is a wood frame building, and unlike the slide on the right, the decision was made in the museum to have exposed wood rafters. So that's a very difficult situation for impact noise. We really rely on having a drywall ceiling. Since that was not desired, we had to come up with a better mousetrap, and in this case we found this material called Acousti-mat 3, which is a woven wire mesh not unlike Entangled, and that can be used in a system with Maxon's Gypcrete to achieve a much enhanced impact insulation rating. A mock-up was built, tested, and the owner concluded that yes, we should proceed with this as opposed to just leaving the floor alone. This did create certain problems because we raised the floor elevation up approximately 1.5 inches or 2 inches, and there were certain ramifications to that, as you can imagine. We also have Doyle Drive, which has been recently rebuilt, and we have in this project windows very close to Doyle Drive, as you can see here. And earlier you saw the improvement using an interior jockey sash, and that is indeed what we have. Here's a close-up on the left, and you can see we used a 1/4-inch laminated glass, and on the right you see the exterior appearance. On the right-hand side is the new theater in the Disney Family Museum, and on the left is the air handler. Earlier we were discussing how mechanical equipment needs to be quieted. In this case, this air handler is directly beneath the theater, which is in the basement, so there's a sub-basement that the air handler lives in, and we had to apply sound attenuators, duct lining, and even a room enclosure around the air handler to make sure that it did not radiate sound into the theater above. Another project that we worked on with ELS Architects is St. Mark's Church here in San Francisco. Here the issue was much different. It was to keep the long reverberation time for a brand new organ. This is a tracker organ. It was installed in the balcony, and all of this really was part of a seismic retrofit. The building was unreinforced masonry. It's been reinforced as part of this project. So here you can see on the left a shot of the nave, and then another picture looking back up before the organ was installed in the balcony. There's a fellowship hall below, and there was an impact noise issue as well as airborne noise issues between the sanctuary and the fellowship hall below. So the solution there was relatively straightforward. We put in resilient channels and a couple layers of drywall and bad insulation, which was a pretty good improvement over the old plaster ceiling and no insulation and no resilient channels. So in summary, we've been talking about room acoustics and reverberation. We've talked about sound isolation, or the attenuation of sound through building walls, floors, and ceilings. We've talked about the impact of environmental noise on building shells and facades and need for better windows and doors, and good gasketing in particular. And finally, the building systems noise, from anything from elevator equipment to ventilation equipment, plumbing, all of that should be considered. So I'm going to discuss the AIA Learning Objectives. Remember that the STC and NIC are ASTM standardized under E90, and these relate to sound isolation. The NRC rating is on a scale of 0 to 1 and talks about the absorptivity of a material. NC, noise criteria, and A-weighted sound pressure level, or dBA, are both loudness ratings. ASHRAE is the definer for NC and RC, which is room criteria. They're both noise ratings. Reverb time is really the liveness of a space. And finally, sound flanking is what we're trying to avoid. We don't want to have excessive leakage through air holes and the like. Finally, I want to mention that what we have, in 1998, produced a book which is largely still relevant today. Maybe only the audiovisual chapter has changed in significant ways, and even that, the planning aspects are still the same. But if you're interested in acoustics, this book is neither a coffee table book, nor a reference book, nor a textbook. It's sort of a combination of all three. So with that, I would like to thank everybody for listening to this webinar and turn the control back over to Cindy. Thank you.
Well, thank you very much, David and Amanda. We have a lot of questions, so I'm going to start with the first one in order that we received them. First one is, how does old plaster compare with new drywall?
Okay, well, old plaster was typically put on lath, and if you're just talking about nailing the drywall to the framing, it's probably pretty comparable as long as the density and thickness are similar. In other words, the mass. There's one exception. There is something called acoustic plaster, which is designed to be porous. And it was also invented in the late 20s, around the time these film palaces were built, and it was improved steadily through the 1930s and 40s. Some of these old buildings, however, although they may have sounded okay when they were new, the excessive painting has sealed the porosity, and now it is reflective, no longer absorptive.
Yeah. Well, this actually is a good segue to the next question, because how does the sheen in the paint matter?
It doesn't.
Okay, but then the paint itself could affect the sound absorptive qualities of the substrate.
Yes, if I would say not on drywall or a reflective material, but if you're painting a sound absorptive product, you need to be very careful.
Mm-hmm.
And there's only one product that I know of. Unfortunately, I can't recall the name of it right off the top of my head, but there is a company back east that makes a paint that is specially formulated for painting acoustical tile once. You can't do it twice.
Interesting. Okay, second question is, how do light gauge metal studs compare with wood framing, or wood studs in framing?
Well, as I alluded to, a 25 gauge stud is comparable to a wood framing member with a resilient channel. Heavier gauge studs, so 20 gauge studs, are really pretty similar to wood studs.
Okay. Next question involves plywood. So many modernists use plywood sheets to complement other surfaces such as plaster walls. What impact does plywood have?
Well, there are two things it could have impact on. It could be considered in the absorptive landscape and the reverberation time landscape. And it's probably as reflective as drywall. It's very nearly the same. However, it is not as massive. It's almost as massive, but not really. So in a multi-layered assembly, we will allow the replacement of a layer of gyp with a layer of plywood. But really, to get the same amount of mass, we would need to make it thicker. So if we had 5/8 drywall and we were replacing it, we should use 3/4 inch ply. There's another issue with wood surfaces. If you're doing a music hall, we love wood surfaces because musicians and audiences identify with wood and music. But if you put thin wood, plywood panels or wood veneers over framing directly, it doesn't have enough mass, and it'll absorb the bass frequencies, and it'll actually destroy the warmth quality of the bass in the music hall. Now, as regards, like I said, for transmission purposes, if you increase the thickness of it a little bit and you're replacing the drywall, that's fine and dandy.
Okay. Next question is, what is resilient channel? You've mentioned it throughout the program. I think some of our audience isn't really familiar with what that component is.
Sorry about that. It is when you take the framing and you, instead of attaching the chipboard or whatever you're using directly to the framing, you add a resilient channel, and it's basically just metal, like light gauge metal channels that run across your studs. horizontally, and you clip your gypsum board onto that instead of straight onto the framing, and it adds some acoustical separation and isolation.
Okay.
They're somewhat misnamed, actually. What they do is if you put your drywall on a stud, you get a line contact between the two, but if you use a resilient channel, you're only getting point contacts. And it's the energy flow through the contact that really makes it work. There really isn't too much resilience to it, actually.
So getting back to one of your case studies, specifically the Ghirardelli square, could you describe how you seal that juncture between the intersecting walls, the drywall assembly that adjoins the masonry wall?
Yeah, so that's going to be done with just a acoustical sealant that's non-hardening, permanently flexible acoustical sealant. Because we were able to identify such a pretty obvious flanking path, it was pretty easy for the contractor to go back in and just fill in all those gaps in the brick with a bunch of acoustical sealant.
Yeah, I think it's important to note that there is a difference between a caulk and your acoustical sealant, that the acoustical sealant is not hardening.
Yes, exactly. It's a non-hardening, permanently flexible type sealant. Yeah.
Right. And next question is related to the map that you showed that's used for urban planners. Can you give an example of how that map would be used, how urban planners would use that map?
Yeah, so when you look at that map, it's going to look kind of like a topography map, and the lines that are closest to, say, like a highway or a railway are going to be labeled maybe like 70 dBA or 80 dBA, whatever they're measured at. And you'll see as you get further away from that, the lines are lower and lower numbers. And so the planner can go back and use that chart. They're usually published, I think, some cities publish that chart.
In California, every municipality is required to have a general plan. As part of the general plan, they're required to have a noise element, and it's required to be updated every 5 years. So they have to commission an environmental or acoustical engineering firm to go out and verify those contours. Mm-hmm. And I'll say they don't always do it, but that's what the law says they're supposed to do. And those contours can be used by the planner, particularly now with the Cal Green Code, where it says, and you can correct me if I've got this wrong, when you're inside a 65 DNL contour or CNEL contour, they're really the same. Day-night noise level is an average noise level, and community noise equivalent level, CNEL, is also a 24-hour average noise level. When you're inside the 65 contour and up, that triggers the requirements of the Cal Green Code, which says you must put in either STC, I think it's 40 windows, in a prescriptive way, or you can do a noise study, and it tells you which sound levels for a maximum hourly sound level average you must meet. So you can do a calculation. It's usually better to do the study than it is to use the prescriptive method, but either one is available to the architect. But that's how the planner identifies that that section of Cal Green Code applies. He says, aha, your building's inside the 65 CNEL contour. The other thing the planner does is there was a chart we showed earlier, which was really a planning document that should be part of the noise element. And that had on one axis different building types, and then it showed 55, 60, 55, and so on, DNL, and it's told three things: normally acceptable, acceptable with an acoustical study, and typically unacceptable. So it has categories so the planner can see if your building type, how it compares to the site as predicted by that contour map.
Okay, we have actually two other questions that relate to windows in buildings. The first one is going back to your example case study on the Hallidie building. What is the interior window sash made of, and how is it attached, and is it presumably reversible?
It is reversible. It would be very easy to take out. I wouldn't want to do it personally, but it can be done. All it is the building has a detail that there's this large concrete lintel or beam that occurs on every floor, and it steps up about 2 feet. And it is very wide. It's kind of unusual. You can walk between the glazing there. I would say it's about 2.5 feet of airspace in there. So we have the original glazing, which is currently being replaced, I might add. After 100 years of service, it was quite corroded. The steel sash system out there was quite corroded, and they've replaced the fire escapes, and it's been an ongoing project. The interior glass is simply in a glazing channel sitting on that concrete lintel and then going up to a gypsum board soffit, and then it just seals out against the full-height gypsum board walls where they intersect.
Okay.
It's just ordinary glass in that case because we have such a huge airspace. It's just tempered glass. It's not laminated because we had this 2-foot airspace. And originally we had about 20 dBA of noise reduction because the facade had so many air leaks. And it was just horrible when the fire trucks would come by. And we used to have a lot of diesels idling in the mornings. That's not so much anymore. It was a really big difference to we basically cut the sound level down by 2 halvings. We made it half and then half again. And so we got an additional 20 decibels of noise reduction. It was really well worth the money.
Good. So you have one large double pane window.
We do.
Yeah. And our next question actually is related to double pane windows, and it's what is the noise efficacy of double pane versus laminated glazing for windows?
Okay. So you may have heard of damping or viscoelastic damping. It's kind of an esoteric field, but damping always controls the velocity, the particle velocity of the panel. And it turns out sound pressure is directly proportional to velocity. So damping can be an important thing for us. When you laminate glass, you're adding damping. And it turns out when you're dealing with a monolithic piece of glass, that's the only thing you can do other than make it thicker and double its mass that way. You get, by laminating, probably a 3 to 4 dB improvement versus, say, doubling the thickness, which would give you maybe a 4 to 5 dB improvement. Now, that compared to, just a single glazing compared to, say, thermal insulating glass. Thermal insulating glass is interesting because it thermally, I'm told, requires a very small airspace, at maximum an inch, typically a ½ inch. That's problematic for us. It introduces low-frequency resonances, and we have seen it resonate at frequencies like 160 hertz and then with harmonics of 320 and 640, and it sounds like a haunted house, especially if the sound source, like traffic, is moving and coming and going. It causes it to modulate, and it can sound a bit like plumbing noise also. So the solution for that, and you get it, by the way, I'm going to say roughly STC 24 to 28 with a standard ½ inch thermal insulating glass assembly, which is not that great. If you substitute in a piece of 1/4 inch lam, now suddenly with this window closed and good seals, you can get up to maybe STC 32, 34, maybe 36 if you have a 1-inch air gap in there. The air gap only starts getting good for us at really above an inch. So if you're wanting to compromise between thermal and acoustical, go to that 1-inch clear airspace. Hello?
Mm-hmm.
Oh, can you hear me now?
Oh.
Yes.
Oh, yeah.
Sorry, we had fire engines going by.
Okay.
What type of acoustical cloth would you recommend for an 1890s town hall with wood floors, smooth walls, and a ceiling?
So I'm going to have you repeat that. What kind of cloth?
Acoustical cloth.
Right. You're going to put that over sound-absorbing material, I presume. Well, the standard of the industry is the Guilford FR701. So if you get a sample of that and you blow air through it, then take whatever else you want to use and blow air through that. The nice thing about the Guilford product is it's not super expensive and it's fire rated. And fire rating is very important in places of assembly, as I'm sure you know.
Okay, we have one more question, and what is THX?
Oh, THX, there's many versions of what it is. Tom Holman's experiment, or is it after George Lucas's film, THX 1138? Lucasfilm, back in the early 80s, George Lucas was on a program to improve cinema. And so he started an audio effort with Tom Holman and THX to dramatically improve film sound. And when they introduced it in about 1984, they had achieved their objective of dramatically improving film sound along with the aid of Dolby. He also, just as a side note, at that same era, started a digital audio group, and it was called, I believe it was called DroidWorks, and then there was another group started called Pixar. George Lucas started a lot of interesting businesses.
Okay, well, we have no other questions, and I want to thank both of you for participating in this webinar, and I want to thank everyone for joining us today. You will receive an email with a link to a survey and a link to a PDF copy of this presentation. We actually sent one to you yesterday with notes. We would appreciate any feedback on this webinar and recommendations for future topics. If you're not a member of the California Preservation Foundation, we encourage you to join us as an individual, nonprofit, government, or corporate member. Each member receives benefits, including discounts to all of our programs, such as these webinars, workshops, conference and awards programs, and our members-only tour. We have our members-only tour coming up on Sunday, February 24th of historic Schramsberg and Chateau Montelena, two historic wineries in Calistoga in the Napa Valley. Your attendance at this program helps us fulfill our mission to provide leadership to protect California's historic sites and communities through education and advocacy. If you're interested in being a member, please visit our website and you can register online for any event and become a member. Thank you so much for your support and have a good afternoon.